Welcome to the deep dive. Today, we're doing something a little different. We're not just, reading a book.
No, not at all.
We're launching into what is, I think, the definitive work that really redefined our relationship with the universe.
It has to be.
Excerpts from Carl Sagan's Cosmos. And this stuff, it's more than just science. It's this deep meditation on history, on biology, and really on our ultimate responsibility.
Right.
So our mission today is to just unpack these foundational themes. The nature of science itself, the story of life, exploration, and the very pressing matter of where humanity goes from here.
It's such a necessary journey to take because Sagan, right from the start, he forces you to confront how limited our own perception is. He says the sheer size and age of the cosmos are, and this is his phrase, beyond ordinary human understanding.
And when you start from there, everything else kind of shifts, doesn't it?
It does. When you anchor yourself to that scale, all of the things that dominate our lives, our fears, our national squabbles, they start to look, well, insignificant, even petty.
But it's not meant to make you feel worthless. That's the key.
Exactly the opposite. It suggests that while we're cosmically young, we're also young and curious and brave.
I love that perspective shift. It's not just a fact, it's a challenge. We're tiny, yeah, but we're also the way the universe tries to understand itself.
And the core argument is that knowledge is just prerequisite to survival. Evolution has kind of cleverly arranged things so that understanding is a joy.
That joy is the fuel. But to even start this voyage, we have to basically abandon every ruler we've ever used.
You have to. Talking about space in miles or kilometers, the numbers just become meaningless. They just overload you.
So we have to use the ultimate speed limit, the speed of light. Maybe we should define that yardstick for everyone, just to be precise.
Okay, so in 1 second, a beam of light travels 300,000 kilometers.
Which is, what, 7 times around the Earth?
7 times in a single second. So
Yeah.
light year is the distance that light covers in a year. That works out to nearly 10 trillion kilometers.
Or about 6 trillion miles. And it's crucial to remember as you're listening, a light year measures distance, not time.
A very common misconception.
So using that cosmic ruler, the universe just stuck. It snaps into this terrifying focus. We start by looking 8 billion light years away, toward the edge of what we can see.
And when you look on that grandest scale, you don't see individual stars. You see these faint, wispy patches of light. They're strewn across the dark like sea froth on the waves of space.
And those are the galaxies.
Those are the galaxies, each one a massive system of gas, dust, and billions upon billions of stars.
And the numbers, when you start combining those factors, they just become overwhelming. How many stars are we actually talking about here? And by extension, planets.
The estimate is about 100 billion stars in a typical galaxy, and there are roughly 100 billion galaxies in the known universe.
So you multiply 10 to the 11th power by 10 to the 11th power.
And you get 10 to the 22nd power, 10 billion trillion stars. And the implication is that pretty much all of them have planets.
10 billion trillion potential worlds.
Yeah.
That number alone just forces the philosophical question on you, right? If planets are that numerous and our sun is just this utterly ordinary star, why on earth would we assume that this little planet, Earth, is the only one with life?
It just becomes statistically absurd. The whole perspective demands humility. The idea that life is unique to Earth. It seems far more likely that the universe is brimming over with life.
So we're starting from a position of almost total ignorance.
Deep ignorance.
Ah.
And yet that's what makes the small step of finding just one other world with life so immensely important. Earth is this tiny speck, utterly lost in this vastness, and yet it's the only place we know for sure where matter has become aware of itself.
And that awareness is built on the scientific method. So let's get into that. What Sagan describes as the essence of the scientific enterprise. It's not a list of facts to memorize.
No, it's a way of thinking. Its fundamental characteristic is that it is self-correcting. It's not about finding some final, absolute dogmatic truth.
It's a process.
It's a process driven by the continual and vigorous reassessment of received wisdom. New experiments, new ideas, unexpected data. They constantly resolve old mysteries and, well, they often create new ones. Testability is the engine.
So if it's all about constant refinement, its defining feature has to be openness. And evidence, you have to be willing to look at data that tells you were wrong.
Absolutely. That's the critical distinction between science and dogma. Any hypothesis, no matter how strange, has to be considered on its merits.
Meaning on the evidence. Can you test it?
Exactly. Can you test it? Dogma, on the other hand, it requires belief without evidence. And fundamentally, the suppression of uncomfortable ideas has no place in the endeavor of science?
You can see that struggle so clearly in historical moments like the Velikovsky affair, which the sources bring up.
Oh, that was a huge deal in the mid-20th century. You had these established figures trying to suppress the publication of Immanuel Velikovsky's theories because they contradicted known physics.
But the scientific community's response wasn't censorship.
No, it was the opposite. They fought back by insisting his claims be subjected to rigorous, repeatable testing. The lesson is, if you disagree, you don't shut down the conversation. You engage with the evidence.
And we can see this exact principle at work with one of the biggest puzzles in modern astrophysics, the neutrino problem. It's a perfect case study.
It was a real crisis for a while. Our standard model of the sun, you know how hydrogen fuses into helium, it predicts a very precise stream of these elusive particles called neutrinos.
Almost massless.
Almost. But when our detectors on Earth went to count them, they found the sun seemed to be generating way too few.
Which means one of two things.
Either our understanding of the sun's core was just wildly wrong, or our understanding of neutrinos was incomplete.
So what were the leading ideas to explain this?
Well, one of the most fascinating came from the physicist Frederick Rains. He suggested that maybe neutrinos aren't all the same, that they could exist in 3 different flavors or states.
And our detectors could only see one of them.
Exactly. If the neutrinos were oscillating between these 3 states on their way from the sun to us, we'd naturally only count about 1/3 of what we expected.
And the really mind-bending part of his theory was the implication that these particles might actually have mass, even a tiny bit. Why is that so important?
It's the ultimate link between the tiniest particles and the biggest cosmic questions. If neutrinos have mass, the sheer number of them in the universe means their combined gravity is actually significant.
So if there's enough of them, and they have enough mass,
their gravity could eventually overcome the universe's expansion from the Big Bang and cause the entire cosmos to close.
so a little puzzle about solar particles could literally determine whether the universe expands into cold darkness forever or collapses back in a big crunch.
That's the high-stakes drama of self-correction. And future experiments were needed, and, well, they've since confirmed that neutrinos do oscillate and have mass. But it's that willingness to entertain a radical idea that defines the method.
But this spirit of rational inquiry, it isn't new. We can trace it all the way back over 2,500 years to the Ionian Awakening.
This was a golden age, mostly in the Greek colonies on the coast of Turkey, in Ionia. Thinkers there, like Democritus, they started to believe everything was made of atoms.
Literally unable to be cut.
Right. And they developed these radical ideas that life evolved from simpler forms, that diseases weren't caused by demons or angry gods, but had natural physical causes.
That's a huge and dangerous leap, replacing myth with mechanism, and you see the immediate violent pushback in the case of Anaxagoras.
Anaxagoras was a brilliant guy, a friend of the Athenian leader Pericles. His crime was teaching that the sun was not the god Helios, but a fiery stone, and the moon was just ordinary matter, with mountains reflecting sunlight.
His critics even thought his estimate of the sun's size, that was bigger than the Peloponnesus Peninsula, was just absurdly arrogant.
Yes, and for this perfectly rational physical explanation, he was convicted and thrown in prison for impiety.
For impiety.
For substituting physics for piety. But the source material points out this profound irony about his accusers. They persecuted him for making their god a stone, which was blasphemy.
While at the same time,
they were, quote, so senseless in their adoration of idols as to make a stone their god. It perfectly captures the absurdity of preferring a comfortable myth over evidence you can actually see and measure.
And that really sets up this tragic paradox of Ionian science. They had the method right, skepticism, observation, but their scientific revolution just stalled. Why?
Well, the historian of science, Benjamin Farrington, he proposed this very compelling socioeconomic theory. It comes down to the slave economy.
The people with the leisure time to think the educated elite were the slaveholders.
Right, and since scientific experimentation often involves manual labor,
yeah,
building things, grinding lenses, getting your hands dirty,
it became associated with the enslaved class. It was low status.
Precisely. Manual labor was socially stigmatized. It wasn't work for a gentleman. And this created this profound disdain for practical, messy experimentation. The Ionians were technically gifted. We know they invented things like the key and the lathe.
But the economic motive for new technology was just gone. If you needed something built, you just bought a slave.
It created a chasm between the mind and the hand, an intellectual disaster. And the sources suggest this isn't just an ancient Greek problem. You see similar trends later, like in the decline of Chinese astronomy after 1280. The educated elites just became less willing to value science as an appropriate pursuit for a gentleman.
And there's a modern parallel, too, in what the sources call the political third world, where educated classes might resist working with their hands or challenging the status quo.
If the people in charge have a vested interest in things staying the same, and if they look down on practical work, then the growth of that self-correcting science just gets stifled. It leads to a long mystical sleep.
That mystical sleep lasted for centuries. But when Europe started to wake up, the pace of discovery just exploded. Let's look at Johannes Kepler, who was so central to figuring out our solar system.
Kepler fully embraced the heliocentric universe from Copernicus, but his initial reasons were very much tied to the mysticism of his time.
He saw the sun as a metaphor for God.
He did. He felt it was aesthetically and religiously fitting for everything to revolve around it. So his first attempt was to try and fit the universe into this ancient Pythagorean idea of perfection.
Right, the Mysterium Cosmographicum, this incredibly complex idea nesting the 6 known planetary orbits inside the 5 perfect Platonic solids.
It was beautiful, mathematically elegant. But the hard data just didn't agree. And this is where Kepler's genius really shows. He inherited the unbelievably detailed and precise observational notes from Tycho Brahe.
And unlike the ancients, he chose the data over the dogma.
He did. When Tycho's data proved that planets don't move in perfect circles, Kepler just relentlessly searched for the real answer.
Which led him to his 3 laws of planetary motion, especially that third and final one.
His third law, published in the Harmonies of the World, it correctly lays out the clockwork of the solar system. It mathematically connects the motions of all the planets. They weren't just individual paths, they were part of one coherent system.
Ellipses, not circles. Inner planets moving much faster.
He found the true harmony was in the mathematical regularity, not in some preconceived geometric perfection.
And that precise framework really set the stage for Isaac Newton to explain why it all worked that way.
Newton's story is almost mythical. In 1666, he's just 23, and he's forced into isolation at his family home because of the Great Plague.
His miracle year.
An astonishing year. He invents differential and integral calculus, the language you need to describe change and motion, and lays the groundwork for the theory of universal gravitation.
He realized the force that makes an apple fall to the ground is the same force holding the moon in orbit around the Earth.
It was a monumental synthesis. It provided the why for Kepler's how. It was such a transformative moment that his own mentor at Cambridge, Isaac Barrow, actually resigned his professorship for him. Just recognized his genius and stepped aside.
This whole journey, from Aristarchus first proposing a sun-centered model way back in 280 BC, an idea that was then forgotten for 1,800 years, to Newton, it's the story of Earth just steadily losing its special place in the universe.
And that demotion just continued into the 20th century. Around 1915, Harlow Shapley used stellar distance measurements to show that our solar system wasn't even near the center of our own galaxy.
We were way out on the fringes.
30,000 light years from the core. We'd lost our place at the center of the solar system, and now we weren't even in a good neighborhood in our own galaxy.
Could you just imagine the visual difference if we lived closer to the galactic core? What would the night sky even look like?
It wouldn't really be night. The sky would be ablaze with millions of brilliant stars. Even after our sunset, the core would provide so much light that the sky would never get truly dark. Our current view, a few thousand stars, is because we live out in the quiet suburbs of the galaxy.
And this realization about these huge distances forces you to connect space and time in a way that our ancestors just couldn't. We're literally looking into the past.
That's the core concept. The speed of light is finite. So when we look out at the cosmos, we are not seeing it as it is now.
But as it was.
Right. If you look at a quasar 8 billion light years away, you are seeing the light it emitted 8 billion years ago. You are literally a time traveler witnessing history unfold just by looking up.
So let's shift to the modern architecture that these observations revealed. The big structures. Galaxies, black holes, the Big Bang itself.
Our Milky Way is a classic spiral galaxy. It's slowly turning, one rotation every 250 billion years or so, a cosmic year. And these galaxies are the fundamental building blocks of the universe.
And inside these structures, you get these extreme points of gravity that just defy common sense. Black holes.
A black hole is what's left when a really massive star dies, and its gravity is so powerful that it overwhelms every other force. It crushes the star's matter down until the density is basically infinite. At that point, nothing can escape, not even light.
So if they're invisible, how do we even find them? Like the candidate Cygnus X1.
We look for their gravitational effects on things we can see. Cygnus X1, which is about 10 times the mass of our Sun, is pulling material off a nearby companion star. As that material gets sucked in and accelerates, it heats up to millions of degrees and gives off intense X-rays. That's how we see it.
The book uses this great analogy with flatland to explain gravity as a distortion of space itself. Can you walk us through that visualization?
Okay, so imagine a two-dimensional universe, flatland, as a huge, taut rubber sheet. The flatlanders only know length and width. If you place a massive object like a star on that sheet, it creates a dent, a curvature.
So a little planet rolling nearby isn't being pulled by a force.
No, it's just following the curve in space that the star has created. Gravity is a distortion in the fabric of space-time.
And in that analogy, a black hole is what?
It's the ultimate distortion, a bottomless pit in
Yeah.
that fabric. And if that black hole is also spinning, the math opens up this really wild possibility that it might connect to other places in space-time.
A
A
wormhole.
wormhole that could theoretically take you across impossible distances, or maybe even to another point in time. Highly speculative, but fascinating.
And finally, the Big Bang, the origin story of the universe. What are the two big, irrefutable pieces of evidence for it?
First is the recession of the galaxies. Pretty much every galaxy we look at is moving away from us. This makes their light shift toward the red end of the spectrum, the redshift, a cosmic Doppler effect. It shows the universe is expanding uniformly from some initial explosive event.
And the second piece of evidence is even more profound. The cosmic black body background radiation.
This is a faint, uniform static of radio waves that you can detect everywhere in space. It was discovered by accident in the 1960s. This radiation is the cooled down remnant, the afterglow, of the incredibly hot fireball of the Big Bang itself. It's a constant echo of creation.
But even with that uniform echo, science keeps finding, lumps and bumps in the cosmic fabric. George Smoot's observation of the Milky Way's velocity is a great example.
Right. Smoot and his team saw that the background radiation wasn't perfectly symmetrical. And this slight anomaly implies that our entire local group of galaxies, including the Milky Way, is streaking toward the Virgo cluster of galaxies at more than 1 million miles an hour,
We're being pulled by something massive.
pulled by an immense concentration of mass. It suggests the Virgo cluster is just part of a much bigger supercluster, stretching across maybe 1 or 2 billion light years.
So the early universe wasn't as smooth as we thought.
It was lumpier, which forces us to rethink the initial conditions and even raises these highly speculative ideas about whether there could have been 2 or more nearly simultaneous Big Bangs.
Okay, let's move from the biggest structures down to the smallest ones that give rise to us. Let's talk about life. It's amazing how the sources stress the molecular unity of all life on Earth. A human and a redwood tree seem so different.
On the surface, sure, but down deep at the molecular heart of life, we are all essentially identical. Every organism on Earth uses nucleic acids for heredity. They all use proteins as enzymes, and critically, they all use the exact same genetic code book to translate that information.
And that shared codebook is the smoking gun for a shared ancestry.
It points unambiguously to a single common origin very early in Earth's history. And the star of that show, the miracle molecule, is DNA.
Can you give us a sense of the information density of DNA? How much data are we carrying in every cell?
It's a full blueprint. All the instructions for making a complete organism, if you were to write out the information in human DNA in plain English, it would occupy 100 thick volumes. A massive library in a microscopic structure.
And its most incredible function is self-replication. With just phenomenal precision, this is all overseen by these amazing molecular machines.
It's a chemical ballet. It starts with an enzyme called helicase, which unwinds the double helix, basically unzipping it. Then DNA polymerase comes in and supervises the attachment of new building blocks to the template. It's incredibly fast and precise.
And the text says that biologists even call one of the polymerase's functions proofreading.
They do. It ensures that mistakes, misplaced bases are corrected almost immediately. But here's the beautiful irony. The engine of evolution, the slow process of adaptation, is a rare failure of that proofreading.
A mutation, a rare error, introduces a change that gets passed on, and that drives evolution. Let's look at how that selection process works, contrasting what humans do versus what nature does.
We can start with artificial selection. A classic example is the Hike crab from the coast of Japan. This crab has a shell pattern that looks uncannily like the face of a fierce samurai warrior.
And the local fishermen, because of superstition and reverence, wouldn't eat any crab that had that face.
Exactly, they throw them back. And by doing that, generation after generation, the fishermen were acting as an external selecting force. They were ensuring that the genes for the samurai face pattern were the ones that got passed on. They unwittingly created this adaptation.
Natural selection is the same logic, but the pressure comes from the environment, not from people.
Darwin and Wallace's core insight was pretty simple. More individuals are born than can possibly survive. So the slightest advantage in one being over those with which it comes into competition, better camouflage, more efficient digestion, whatever it is, that will turn the balance in favor of survival.
There's a perfect little anecdote about this in H.J. Muller's genetics lab. It really shows how subtle and constant this process is.
So the narrator is working in Muller's lab studying mutations in fruit flies, Drosophila. One day, they find this creature under the microscope that's just radically different. Prominent wings, long feathery antennae. It looked like a massive evolutionary leap in one generation. The student was ecstatic, thought they disproved Muller's idea that evolution is slow.
And the humbling realization was, what?
Muller just smiled. He explained it wasn't a fruit fly, it was a moth. Specifically, a species of moth that had evolved to adapt to the unique environment of a genetics lab.
It was eating the molasses meant for the flies.
It was. The mother moth would perform a dive-bombing pass, dropping her eggs on the run. In the brief moment, a technician opened a container. It was this lovely adaptation in nature, the product of micromutation and natural selection. Life just fills every available niche.
This ability for life to emerge brings us back to abiogenesis, the chemistry of creation. How do you get complex organic molecules from simple stuff?
The key thing is that lab experiments show this isn't some magical process unique to life. When you simulate early Earth conditions, zap a mixture of simple gases like methane, ammonia, water vapor with sparks, you quickly produce a whole variety of organic molecules that are relevant to the origin of life.
And the huge philosophical takeaway here is that since those initial ingredients and energy sources, lightning, volcanoes, UV light, are common everywhere in the cosmos,
The conclusion has to be that the molecules of life fill the cosmos. The simple chemical reactions that led to our building blocks must have happened on a billion other worlds in the Milky Way galaxy alone.
we're not special because of our raw materials.
No, we're only special in how those materials arrange themselves. And if the molecules are everywhere, it lets us speculate about what alien life might look like, even in a place that seems impossible, like Jupiter.
Jupiter's a gas giant, no solid surface. Life would have to be atmospheric. The big threat would be turbulence, right? Getting carried down into the deep, hot layers and getting fried.
Buoyancy would be everything, so you can speculate about what might evolve. Maybe you'd have these floaters, huge bag-like creatures, maybe kilometers across, like giant living balloons moving in vast herds.
And where you have peaceful grazers or floaters, you have to have predators.
You have to have hunters. They need to be fast, maneuverable, streamlined. They'd consume the floaters for their organic molecules and hydrogen. Now, this is all just speculation tempered by the laws of physics and chemistry, but it achieves a vital goal:
Which is?
to deprovincialize biology. By forcing ourselves to imagine life that isn't based on our specific carbon and water template, we expand our mind for what might actually be out there.
Now we go from speculation to actual execution. Let's look at the tools we use for this exploration, the evolution of the rocket.
It started with the ancient Chinese and gunpowder, but the real scientific path began with theorists like Tsiolkovsky, then Robert Goddard, who first developed liquid-fueled rockets.
He was ridiculed for his ideas about going to the moon.
Totally ridiculed, but his innovations were crucial. They led to the German V2 and eventually the Apollo program. The things Goddard dreamed of, orbiting stations, probes to Mars, they've all been fulfilled.
And our first missions quickly tore down our old, comfortable theories about our neighbors, starting with Venus.
Early on, we couldn't see through its clouds, and we couldn't detect any water vapor, which led to some wild speculation. Some thought it was covered in oceans of seltzer water.
Others thought it was a global oil field.
Right, but the reality that radar and the Pioneer Venus mission revealed was far more terrifying.
A hellscape.
A total hellscape. Massive mountains, rift valleys, and crushing heat. A world where rock flows like taffy. The key discovery was the runaway greenhouse effect.
How does it work so intensely there?
Sunlight gets through the clouds and heats the surface. The surface then tries to radiate that heat back out as infrared light. But the atmosphere, which is 97% carbon dioxide, plus water vapor and sulfuric acid clouds, is almost perfectly opaque to infrared.
So the heat gets trapped.
It gets trapped and just builds and builds until the surface is hot enough to melt lead. It's a serious cautionary tale for any planet with too many greenhouse gases.
Moving outward, we have Mars, always the focus of our hopes for finding life, which led to the incredible Viking missions.
The Mariner 9 probe had already shown us Mars's history, these sinuous channels, floodplains, undeniable evidence that liquid water once flowed there, implying a totally different ancient climate. That's what fueled the urgency for the Viking 1 and 2 landers.
And the planning for Viking was just meticulous.
The safety constraints were immense. The landing sites couldn't be too high, or too windy, or too hard, or too soft. Viking 1 landed in a place called Tracy, a plain near a confluence of old channels. And after a year and a half traveling hundreds of millions of kilometers, the landers performed perfectly. Heat shields, parachutes, retro rockets, and they touched down gently and safely.
But the results from the little biology experiments they carried were just ambiguous.
Frustratingly so. Some tests suggested metabolism, but others could be explained by simple chemical reactions in the strange Martian soil. This ambiguity is why the sources stress we need a sample return mission. We need to get Martian soil back to our big, sophisticated labs here on Earth.
And the most promising place to look for life isn't even on the surface, which is blasted by sterilizing UV light.
Exactly. The focus has to be subsurface. The text mentions Imre Friedman's work in Antarctica, where he found algae living 1 or 2 millimeters inside translucent rocks. The rocks trap a little liquid water and block the worst of the UV. If life is on Mars today, it's probably hiding inside rocks or deep underground.
The complexity of Viking was really just preparation for the grandest journeys of all, the Voyager missions to the outer solar system.
Voyager 1 and 2, launched in 1977, were just triumphs of robotic engineering. Semi-intelligent, nuclear-powered, weighing almost a ton, and built with all this redundancy to survive the journey.
The process of getting a single picture back from, say, Jupiter's moon Europa 500 million kilometers away is almost unbelievable. Can you walk us through that?
Okay, so sunlight bounces off Europa and hits the Voyager camera. The onboard computer converts that image into a digital signal, ones and zeros. That radio signal is beamed across hundreds of millions of miles to the Deep Space Network stations on Earth, these huge radio telescopes in Australia or the Mojave Desert.
Then it has to be processed.
Right. It's relayed by satellite and microwave to the Jet Propulsion Laboratory in California. The final image is reconstructed pixel by pixel from a million digital dots. That whole relay demonstrates this incredible human collaboration.
And the discoveries were immediate and revolutionary, especially with Jupiter's 4 big moons. Let's start with Io.
Io was already known to be weird, the reddest object in the solar system. Voyager showed us why. It is volcanically active, with the fastest geological changes we've ever seen. We saw massive plumes erupting, like from the Prometheus volcano, spewing sulfur hundreds of kilometers into space.
And what's driving that intense volcanism?
Tidal flexing. Io is caught in this gravitational tug-of-war between Jupiter on one side and the other big moons, Europa and Ganymede, on the other. This constant squeezing and stretching generates massive internal heat, melting the interior and driving the eruptions.
The other big icy moons, Ganymede and Callisto, they presented a different puzzle based on their density.
Their density was calculated to be low, about halfway between rock and ice. So scientists predicted that internal heat from radioactive decay over billions of years would get trapped, creating internal layers of slush and water, subsurface oceans.
And Voyager confirmed it.
The images showed these unique, non-cratered icy features that implied internal, water-driven geology had reworked their surfaces.
And finally, what could Voyager tell us about the inside of Jupiter itself?
Deep inside that gas giant, the pressure is just staggering, 3 million times Earth's atmospheric pressure. This extreme pressure squeezes the electrons right off the hydrogen atoms, forcing the hydrogen into a new state of matter. Liquid metallic hydrogen.
It acts like a fluid metal.
And it can conduct electricity, which drives Jupiter's massive magnetic field. And hidden at the very center of that vast, sloshing ocean of liquid metal,
An Earth-like world.
a lump of rock and iron, maybe 10 times the mass of Earth, hidden forever in a pressure vise, an inaccessible secret at the core of this giant planet.
Every single step of this exploration, from realizing there are 10 billion trillion planets to seeing volcanoes erupt on Io, it all just reinforces one profound truth. Earth, from the cosmic perspective, is poignantly beautiful and rare. It's the only world we know where matter has become alive and aware.
And that realization puts this immense moral weight on us. We now have the technological power, driven by our incredible minds, to fundamentally change the climate and the destiny of this entire planet. The vastness of space shouldn't make our world seem small. It should make us cherish it.
We owe this awareness to the long, messy evolution of the human brain. The source uses Paul MacLean's model, which divides our brain into three layers reflecting millions of years of history.
MacLean's idea is that the brain evolved from the inside out. The deepest, most primitive part is the brainstem, which just controls the basic rhythms of life: respiration, heartbeat. Surrounding that is the R complex, which we share with reptiles.
And the R complex is where our primitive, non-rational drives live.
It governs aggression, ritual, territoriality, social hierarchy. Sagan vividly calls this the brain of a crocodile. It's powerful, ancient, and often deaf to logic.
And then layered on top of that, we get the mammalian brain.
The limbic system. This is the source of our moods and emotions, especially that crucial evolutionary drive for concern and care for the young is what gives us empathy. And finally, sitting in an uneasy truce with these older systems is the cerebral cortex.
The seat of critical analysis, consciousness, civilization itself.
This is what makes us human. It's where we do math, compose music, create philosophy. It's a mechanism of liberation, allowing us to break free from the genetically inherited behavior patterns of the R complex. When we think rationally, we're using the newest part of our brain to control the ancient, often murderous impulses of our past.
And if our brain's capacity is huge, 10,000 times the information in our genes, we've augmented that power exponentially with the invention of the book.
Books are magic. Our genetic library is maybe 1,000 thick volumes. Our brain holds 10,000 times that. But the great libraries of the world contain the equivalent of 10 times more information than any single human brain.
They break the shackles of time and death.
Writing was invented just 5,000 years ago. But books let us connect with the wisdom of ancestors across almost 100 generations. The trick is knowing which books to read, but the possibility of tapping into all of human history is what modern civilization is built on.
Unfortunately, that technological power from our cortex is now paired with this terrifying potential for self-destruction. Nuclear war, driven by the impulses of the R complex.
This is our critical crossroads. We're a species that can travel to the edge of the solar system, but we're still driven by mistrust and short-term thinking, which leads every technological state to plan for nuclear war, even when everyone knows it's madness.
The analysis brings in L.F. Richardson's work, which links individual violence to global war as a single spectrum.
Richardson's conclusion was stark. War is murder writ large. It's on a continuum that connects an individual murder to all-out war. The psychology is the same. Nations, just like people, when their illusions are threatened, fly into murderous rages. We've just organized our reptilian aggression on a global scale.
And the consequences of a full nuclear exchange go way beyond the immediate blasts. What are the subtle global effects?
The first is the atmosphere. The intense heat from thousands of nuclear fireballs would create massive amounts of nitrogen oxides. These would get injected into the stratosphere and destroy a huge chunk of the ozone layer, our shield against solar UV radiation.
The resulting surge in UV would be lethal.
For years, it would cause widespread skin cancer, massive crop failure, ecological collapse. On top of that, the radiation itself would suppress our immune systems, leading to devastating plagues among the survivors.
And the long-term genetic damage.
Lethal mutations, damaging the genetic heritage of our entire species. The survivors would face a ravaged biosphere and the hopeless sense of a civilization destroyed for nothing. The damage is so much greater than just the immediate casualties.
The sources have this stark budgetary comparison that really throws our priorities into focus.
In 1980, the U.S. Department of Defense budget was $153 billion a year. The budget for the Arms Control and Disarmament Agency, which was dedicated to preventing this disaster, was just $0.018 billion a year.
The disparity is massive.
A truly rational society would treat war, as Einstein called it, like an illness of childhood. And you'd invest massively in understanding and treating it, not just preparing to execute it.
This brings us back to the cosmic perspective and the search for extraterrestrial intelligence framed by the Drake equation. The fact that we haven't been visited, the Fermi paradox, it suggests a great filter exists.
The main question is, why don't we see clear evidence of alien life? The equation includes the factor L, the longevity of a technological civilization. The non-observation of visitors suggests either that such civilizations are incredibly rare, or much more likely they are generally unstable.
So survival itself, factor L, is the ultimate test. What does a civilization need to do to survive for a long time?
To reach an interstellar phase, A civilization has to navigate the gauntlet we're in right now, avoiding greed and ignorance, pollution, and nuclear war. If we're categorized in a hypothetical Encyclopedia Galactica as a certain type, with fossil fuels, nuclear weapons, organized warfare, our probability of surviving another 100 years is estimated at a grim 40%.
And the text makes this very powerful conclusion about what it takes to explore the stars. You can't do it if your own house is on fire.
That's it exactly. Any civilization capable of serious long-term interstellar missions must have achieved zero population growth or something very close to it for many generations. They have to master resource management and planetary stability. Otherwise, all their resources get diverted to just sustaining a growing population at home. The biggest filter isn't technology, it's political and sociological.
This whole deep dive has really been, as promised, a voyage of self-discovery. We are literally made of stellar ash, and our intelligence is this fragile, recent thing, housed in a brain that's still in an uneasy truce with its primitive, aggressive past.
We are at that critical crossroads. We have the intelligence in our cerebral cortex, and we have the collective memory in our libraries to unify our planet peacefully. But it has to be a conscious choice, made against the powerful pull of the R complex.
The philosophical challenge that runs through this whole thing leaves us with this inescapable responsibility.
The challenge is clear. If we do not speak for Earth, who will? If we are not committed to our own survival, who will be? The cost of survival and eventual cosmic exploration requires us to apply our intelligence to avoid self-destruction. That's the highest calling of the human mind.
And as we think about our future, let's remember our current status in the cosmic neighborhood. We launched Voyager, the most ambitious physical message we've ever sent.
And Voyager moves with the slowness of a race in a dream. It'll take tens of thousands of years to reach the nearest stars. It carries that golden record, a carefully curated message. But get this. Our everyday television signals, moving at the speed of light, will overtake Voyager in a matter of hours. Those signals will reach Alpha Centauri in just 4 years.
So we are already announcing ourselves to the universe with every show we stream, every news report.
That unfiltered signal of our current civilization, our wars, our rituals, our triumphs, our anxieties, it's spreading across the light years right now. And the profound, lingering question is this. If, in a few decades or centuries, someone out there picks up those broadcasts, what will they conclude? What kind of civilization is currently speeding toward the stars? We can only hope that they will think well of us.